the YAML for the model language, because in contrast to, I think, what was said yesterday, I think the model language is very easily readable, even without having read the specification. But writing is almost impossible, because there are often many options to express something, or you don't know what the parameter names are. So generally, the model language is based on one non-optional entry, the stack, which describes some kind of order of the system, coming with the beam, as Jochen always said, as defined in optics, the beam always comes from the left. So you basically first come from the ambient layer, then whatever comes in between, and you end up at the supporting substrate layer, or whatever is on the other side. To keep it as simple as possible, there are some rules on how things are resolved. So in general, this can be a name here, but if as the name you put something that is known material, or that is an element, it will be resolved to that material. So you don't need to specify all of that in advance. So you see the other attributes here, a substack. I will come to that a bit later. Then you can specifically define layers with all parameters, and specifically define materials or compositions. And then there are some global parameters that are set by default that you can override, that apply then for everything. For example, we have a global standard roughness that's assumed. That's, I think, 3 angstrom. And you can override this, and if you don't write anything else to your layer, this will be taken. So this is now the simple iron 100 nanometers. So that's one of the globals also. What's the unit of the length? And the default is nanometers. So if I say update model here, this will evaluate it. And this is what this string basically represents. It's creating a layer silicon, a layer iron, and a layer vacuum. This is the neutron reflectivity from that, and this is the SLD profile from that. Or you can also see it for X-ray. So where this comes from is now iron is in the SLD database. So it's looked up, and just the density is taken from there to define the depth profile. We can also then define, for example, a second layer here, and directly extend it. There's a possibility to group certain layers into these substacks, and they can, for example, be repeated. Let's say we make 3 times. Now this is resolved to the substack and the layers inside that are repeating. You can play this game as long as you want. So we can put this again in a substack, make it 2 times, and add, for example, some strange interlayer in between. Now you're getting a upstack and a substack. This can be deep as you want. And you can also define this as a named system. For example, I call this all. And now I can here enter substack, then it creates from the definition of the class all the attributes needed, and makes a comment here what is actually needed to put here. So we had 2 repetitions here, and the stack string looks the same as the global one, would then be this. So I would now expect, if I evaluate that it should give the same result. If I don't make a miss. I have to name it, sure. So now this all here refers to this word. And these names can be any of the lower defined items. It can be a substack, it can be a layer, it can be material. Then the layer is basically taken with that material. But this gives a lot of flexibility, makes the resolution of the model for the program not that straightforward, but I think it makes it easier to write and read. So this is all now in ORSO, so the resolution doesn't have to be done by your program completely. So the ORSO object allows the program to calculate what is actually in there. For example, you don't have to support individually substack depth of infinity. You can say, just make me layers out of it. And this is how I create the SLD here. This is just refnx calculating reflectivity and SLD from the layers that I can automatically generate in ORSO from that. Then to the globals. If I enter that, you see here now the roughness that I can override the length unit. Let's say I just want to override that everything I wrote was angstrom and not nanometer. Then this can also be resolved. Now it's filling all the default values for the other globals in here as well. So this is where we stand, and I can show a few examples of that that are also in the distribution of ORSO, I think. So this is just a 10 times multi-layer iron silicon, and you can see nicely how this creates the Bragg peaks. And here's some examples on how to define the materials specifically. So you can define materials by formula and density, or by scatter length density, like here. Or what I added now in the update is you can also use SLDDB IDs. So if I say here, this is instead of iron 70, ID equals 100. I have no idea what material that is, but then it looks it up in the SLDDB with that material number. Material names should also work now. We have to think about if this is what we want or not. And I think this can now basically describe everything that is a slab model of known materials quite well. You can also mix things. Here's how layers are defined. So you can, for example, just give a layer a name and write the thickness here and the material, but you can also then add the roughness parameter, or in materials, you can also add magnetization, for example. So now to how to extend this. So if you are working in a field that doesn't know much about the layers, like if it's not a epitaxially grown film, but it's some kind of soft matter material or some mixing system, you might want to describe it with something that's more physical, but not obviously a single layer. Can be multiple layers or whatever. And so I was trying to make this still compatible with YAML, compatible with the ORSO header formats we have, but enough flexibility to allow almost everything. And the idea was to, instead of allowing for substacks just repetition of something, having a class that describes what I think we're talking about when I entered. What is the physics of this and this leaflet, for example, and we have defined as ORSO what is the calculation that gives you layers out of that. So our class would basically define the parameters and would define how this is resolved to layers, and then a program either knows what a lipid leaflet is and can interpret the class itself, or it doesn't know and can ask the class to make layers out of it. So for that, I have an example here of something. Oh, that's not it. of something that uses a class that I call function to elements. So this basically, instead of a substack, you write something that has always the parameter substack class with the name that defines where you have to look for the definition. And then here for this substack class, it has basically two materials and some arbitrary function string that is evaluated by the depth and gives you the mixing fraction of material 1 to material 2. And here it's basically a linear gradient that is between nickel and titanium. And here for neutrons, you can see, I think the roughness is probably too high. Let's remove it to see it better. So this gives you a sawtooth kind of pattern. So we have one global parameter here that defines the slicing size to be used for these kind of functions. You could override it per gradient, but you can also just make it globally and then it's applied to everything. I can make it extremely fine, then it will probably be a bit sharper, but you don't see it really on the plot very much. And here there's a second new class that I put in that allows you to rewrite something without rewriting all parameters a second time. So this is where I say like. So basically this says this is an object that is like the gradient, but one parameter was changed. The function instead of x becomes 1 minus x. So that's why it's this up and down sawtooth and not just vertically coming down. And I think I have some other nice examples for the how this is applied for that use more or less sinusoidal patterns, yeah, like this. So you can already do very complex things. And in the resolution, you see that this is now shown as a class with all its parameters. And another application of that would be actually based on the lipid leaflet and my hard matter person understanding of RefRNX's use of that. So here I have a data file, an ORSO data file, and I can select which of the data sets to use. So this is basically the example that Andrew, I think, posted somewhere from a notebook that has 3 different contrasts of the same system. And I put them in one ORSO file so I can select which data set. And this is now having an inner leaflet and an outer leaflet. And they are defined by the leaflet substack class with the parameters similar to what RefRNX uses. So this is the area per molecule, if I understand correctly, the scattering length values, the volume, and the thickness parameters. And then this is one that is not reversed. And then we have another one using against this like but statement where it is reversed. So same parameters, just the other way around. And you see those are put together in a substack. And now there's something in addition for this in the stack, putting it in brackets. If you write the keyword in something, then this is used as the standard solvent for whatever needs solvents in there. We could discuss if this makes sense, though there's also a default solvent, and then we could see if it makes more sense to always use the backing material or something like that. But this was my understanding that it is a good idea to not specify the solvent every time you have something, but have some kind of generic. And because both of them use the name solvent, both of them will use the material here. So you only define once the SLD for this solvent, and then it's applied to all of that. And I could say, okay, this is not just one, let's make 3 out of it. And that works. And now, what do I see as the main advantages of using the model language? One of it fits in our header, so we don't need to change any of the ways we store data. And then it's helpful in the experiment planning already, because you enter your sample when you align your sample, or when you write a proposal. So you can use tools like what you see here to calculate what do you expect from the experiment. It helps you afterwards to know what you measured. It helps, for example, AI systems to be able to analyze large data sets. And I think it's most value lies when you start analyzing the data. So if you think you have a data set, you can make your modeling program directly create the model out of it. And for that, to show it off a little bit, I have a viewer for our data sets that I will share now. So now if I open the file that I showed before with the lipid leaflets, now it shows all the data sets here, and you see the data that belongs to it. And now it can show you the model. So we can see the different contrasts, and it analyzes the model for every contrast and already gives you a good idea of how the reflectivity should look like without a large amount of effort. And again, you can see what the model is set up from slabs and so on. So that would be what I have, unless somebody wants a particular model to be shown.